Impossible places. They built the impossible. Now they must keep it alive. China's Xiaolangdi Dam must flush Yellow River silt before it consumes vital flood capacity. Across 30 remote structures, the decisive repair may be the one crews cannot reach. Building in a river gorge across open sea or against a cliff settles only the first problem. Water loads concrete, salt enters steel, rock shifts, ice closes access. Distance turns a minor fault into a major threat because crews, tools, and replacement parts may be days away. These structures stay useful only when inspection and repair never stop. In this video, we examine how engineers keep them operating where every route, surface, and weather front works against the job. Scale hides dependence. Even a concrete barrier more than 2 kilometers long must yield to the river's rhythm every day. At Sanduping, the Three Gorges Dam rises nearly 200 meters, feeding 34 generating units while passing ships and managing floodwater. This is not a static wall. Power production, navigation, downstream flow, and flood protection all compete for the same water. Before seasonal flood risk rises, operators must lower the reservoir at the right time to create storage space. Ships and turbines, meanwhile, need predictable levels and steady conditions. 2 5-stage lock systems and a ship lift add moving machinery to the inspection burden. Spillways, gates, sensors, and navigation equipment must remain dependable under immense pressure. The Yangtze brings sediment and floating debris toward intakes and gates. Accumulation constricts flow, strains machinery, and makes repeated clearing essential to power and passage. The work reaches far beyond the concrete. Changed shorelines and groundwater conditions require monitoring of unstable slopes and landslide-prone banks across the reservoir. Distance adds its own pressure. When a sensor flags movement or a bank shifts, reaching the problem can lag behind detecting it, even as the water keeps changing. The decisive achievement is not the mass itself, but relentless upkeep that keeps turbines, passages, slopes, and gates aligned with the Yangtze's daily demands. A canyon narrow enough to strengthen a dam also leaves almost no room to repair it. Bhutan rises nearly 300 meters between Sichuan and Yunnan, with 16 1-gigawatt generating units buried in powerhouses inside the mountains. Its double curvature arch drives the reservoir's force sideways into steep rock abutments. The canyon walls are not scenery, they carry the load. That geometry creates power, but concentrates risk. Machinery, transformers, tunnels, and controls are packed into a gorge with limited roads, work areas, and alternative access. Building here demanded deep excavation, high-strength concrete, river diversion, and stabilized slopes in a seismically active region. Operation inherits every one of those constraints. Instruments must track deformation, temperature, seepage, seismic movement, and changes in the rock abutments. A small reading can point to a problem hidden inside concrete or rock. Then crews still have to reach it. Steep slopes, rockfall exposure, and narrow access routes turn inspection, replacement, and heavy lifting into carefully staged work. Sediment presses toward the intakes. High energy releases wear spillway surfaces, while transmission equipment must remain dependable beyond the gorge. Bhutan turns the canyon into a giant machine room with no spare space for error. Its scale does not create tolerance. It makes constant measurement and difficult repair the price of keeping 16 immense units online. Xiaolangdi releases the river with force to stop sediment from slowly disabling the dam. Near Luoyang, controlled flows burst through low-level outlets, scouring silt from a yellow river that carries extraordinary loads of fine sediment. When water slows, that material settles. The riverbed rises, storage shrinks, and flood control space begins to disappear. Maintenance here reaches beyond workshops and inspection tunnels. Operators use water as a tool, timing releases to lift deposited material and drive it downstream. That timing cannot be casual. Discharge must match channel conditions because the muddy surge affects banks, infrastructure, irrigation, and communities below the dam. At the same time, Xiaolangdi must retain flood capacity, generate electricity, and supply water. Every release trades one operating need against another. The river also turns the cure against the machinery. Fast sediment scours gates and outlets, so the equipment that clears deposition absorbs the same abrasive load. Inspection and repair must follow that wear, while the next sediment load is already moving toward the reservoir. What stands out at Xiaolangdi is not simply its ability to hold back the Yellow River. It preserves its own operating space by deliberately unleashing the force that keeps wearing it away. A road across open sea survives only by changing form before the shipping lanes cut through it. Opened in 2018, the Hong Kong-Zhuhai-Macau link combines elevated bridges, artificial islands, and a nearly 7-kilometer immersed tunnel beneath busy shipping channels. The tunnel was built from sections floated offshore, lowered into a trench, aligned, sealed, and buried. That solved the shipping problem, but created underwater joints that demand constant scrutiny. Above water, typhoons, tides, and salt spray work on bearings, expansion joints, steel protection, and exposed concrete. Below, seepage and seabed settlement demand a different watch. Traffic underground depends on pumps, drainage, ventilation, lighting, fire protection, and control systems. A fault in any one sends crews into a confined route that may still be carrying vehicles. Artificial islands are not pauses between structures. They are transition points where bridge approaches, tunnel portals, utilities, and marine foundations meet, and where one repair can affect several others. Access becomes part of the engineering. Crews may need lane closures, marine equipment, or carefully timed entry into the live tunnel, while ship traffic and rough water restrict the working window. Here, a continuous road exists only because crews manage several hostile environments as one. Typhoons, salt, settlement, and moving water keep changing the job. Maintenance on this bridge tunnel has no day off. More than 6 kilometers of urban road stand over seawater that feeds corrosion from below and through the air. Qinghai Bay Bridge crosses exposed coastal water in Dalian, placing its deck, steelwork, concrete piers, and approaches in several corrosion zones at once. Salt reaches from both directions. Wind carries it onto the upper structure, while waves soak the waterline and repeated drying leaves concentrated chlorides behind. Protective coatings and dense concrete slow that corrosion. They do not end it. Once chlorides pass through cracks or failed protection, reinforcement corrodes, expands, and pushes surrounding concrete away. That is why inspection follows the places where water collects and movement repeats: drainage outlets, joints, bearings, cable fittings, pier faces, and edges exposed to spray. Many of those points cannot be reached from land. Boats, temporary platforms, or underdeck equipment must carry crews into position, with tides and wind deciding when the work can proceed. Dalian adds winter freezing, humidity, and temperature swings. Concrete opens and closes, joints move, and trapped water turns a small defect into a larger repair. Beneath ordinary traffic, crews keep sealing, coating, draining, and inspecting Qinghai Bay, surface by surface and season by season. Far below the roadway, the Tara River leaves repair crews no usable ground beneath the principal arch. Completed in 1940, Georgievich-Tara Bridge runs nearly 400 meters and rises around 170 meters above the river, with its largest arch spanning more than 100 meters. The canyon offers no convenient support beneath the principal span. Loads travel through the arch into the steep valley sides. The terrain that required this crossing also dictates how it carries the road. That remoteness made the crossing strategically decisive. During the Second World War, one section was disabled to block an occupying force, then rebuilt to restore the mountain route. Moisture enters cracks. Winter freezing expands trapped water. Temperature changes move the deck, and repeated cycles test concrete and reinforcement that have served for generations. Inspection is difficult before any repair begins. Crews must reach arches, piers, deck edges, and the underside, while working high above a deep, protected canyon. Materials, platforms, and access equipment have few easy routes into position. A modest defect can therefore demand planning out of proportion to its size. The bridge carries a mountain road, but history still defines the crossing. At Georgievich-Tara, keeping it open means repeatedly reaching the concrete the canyon makes hardest to reach. A bridge that avoids touching the most dangerous ground still depends on that ground to hold it. Near Randa, the Charles Kuonen spans nearly 500 meters across the Grabengufer ravine, about 85 meters above its floor. The crossing replaced an earlier bridge damaged by rockfall. Its alignment shifts the load into cables and mountainside anchors, leaving the unstable ravine free of supports. The narrow steel grating deck is practical, not fragile. Low mass eases the burden on the span, while open grating sheds snow and lets wind and water pass through. But that openness exposes hardware to moisture and sharp temperature swings. Crews must inspect deck panels, clamps, cable terminations, barriers, anchors, and the components that restrain movement. Footsteps pulse through the deck, and alpine gusts push sideways. Stabilizing cables must control that motion across almost half a kilometer. Inspection begins before anyone reaches the span. Snow, seasonal trail conditions, freeze-thaw damage, and shifting rock can obstruct access or alter the slopes carrying the anchors. Crews then check exposed steel one connection at a time. A fault at a clamp, anchor, or wind brace can compromise the entire crossing. Charles Kuonen is slender only in outline. Keeping it open requires work on a mountain that keeps changing. The bridge's unsettling feature is the part that must earn trust every morning. At Zhangjiajie Grand Canyon, a transparent deck runs about 430 meters between sandstone cliffs, with open air visible beneath each step. The surface is not one sheet of glass. Layered glass panels form replaceable modules on the steel structure, across a deck roughly 6 meters wide. That design isolates a worn or damaged panel for replacement. It also multiplies the edges, seals, supports, and drainage points that demand inspection. Wind crossing the gorge moves the span. Crowds add uneven loads and repeated vibration, so visitor limits and controlled entry become engineering controls. Rain changes traction and visibility. Grit carried on shoes marks the clear surface, turning ordinary foot traffic into slow wear. Cleaning is not cosmetic, and a weather closure is not merely a tourism decision. Both protect the deck while crews assess panels, anchors, drainage, and monitoring equipment. The canyon gives the bridge its force, but complicates intervention. Every replacement panel, tool, and inspection task must be managed on a suspended structure between remote cliffs. Zhangjiajie turns public trust into daily engineering work. Inspect the glass, control the crowd, and verify its condition again. At mountain scale, extra length does not create one larger problem. It creates hundreds of smaller places to inspect. Sky Bridge 721 stretches more than 700 meters between the slopes of Dolny Morava, rising about 95 meters above the valley. Its narrow mesh deck avoids a heavy solid floor. The mesh sheds rain and some snow while reducing the load carried by the slopes. But low weight does not cancel motion. Gusts press across the span, uneven foot traffic shifts the load, and stabilizing parts restrain movement over the full length. Length also expands the inspection route. Crews must trace main cables, then check connections, mesh modules, barriers, fittings, and anchors across hundreds of meters. A fault is rarely close to everything needed for repair. Tools and replacement parts depend on mountain lifts, service routes, or specialized transport. Weather can block access from either end. Snow and ice may make the approaches unsafe even when the bridge itself remains structurally usable. Repair windows narrow under gusts, winter conditions, and visitor demand. Some work requires a closure. Worse weather can then block the crews as well. Sky Bridge 721 makes length a permanent obligation. More steel, more joints, and more points that crews must keep within reach. 14 steel steps descend into empty alpine space, yet the force that shuts them is often invisible. At about 2,700 meters, the Dockstein stairway to nothingness hangs from the Hunarkogel station, with no support beneath its glass platform. The mountain carries every load. Steel frames and anchors drive the weight of visitors, wind and snow back into the station and rock. That clean edge survives through constant attention to fastenings, welds, glass edges, anti-slip surfaces, corrosion protection, and drainage. Winter can strain all of them at once. Ice makes the steps and glazing unsafe. Packed snow blocks outlets, traps water, and can conceal damaged seals or fittings until crews clear the structure. The valley may appear calm, while high winds force a closure above. Weather does not merely interrupt the attraction, it decides when inspection and repair can happen. Every tool, replacement pane, and safety kit depends on the cable car and a usable weather window. If the lift stops, visitor access and rapid repairs disappear together. Construction fixed the platform to the cliff once. Operation means returning after every winter and accepting the mountain's terms. Remove the front columns, and every visitor load must travel backward into the cliff. At about 1,200 meters above the Adriatic, Biokovo's skywalk pushes beyond Ravna Vlaška on steel and concrete anchored into karst bedrock. The glass reveals the drop, but the mountain bears the force. Weight and gusts travel through the frame, into a reinforced base, then into rock. Steel expands and contracts as temperatures change. The glazing seals flex with it, while water presses into every joint. Drainage is not housekeeping here. Water can reach anchorage zones, lodge in connections, or freeze, turning one blockage into a structural problem. Crews inspect far more than glass. Welds, bolts, rail connections, glazing supports, drains, and rock anchors all demand access. Strong gusts can close the platform before work begins. Access creates another limit. A steep, narrow road through Biokovo Nature Park restricts traffic and the size of equipment able to reach the cliff. The structure carries the exposure for everyone above it. Biokovo does not hide the void. Its beauty depends on steel, drainage, anchors, and crews holding that pressure without interruption. Macau Tower removes the guardrail, then makes equipment and staff carry the full burden of safety. The skywalk circles the tower about 230 meters above the city on an open platform only about 2 meters wide. There are no conventional rails, but attachment never stops. Each participant wears a harness and tether linked to an overhead track that maintains the connection around the route. That design turns a short walk into repeated inspection. Staff check webbing, buckles, tethers, connectors, tracking trolleys, anchor points, and the exposed floor. Wear cannot be negotiated. Equipment must be cleaned, serviced, documented, and removed from service when wear exceeds limits. The tower stands in a city, but its outer edge remains a severe operating environment. Wind challenges balance, rain cuts traction, and lightning or harsh weather can halt the entire route. Human control is just as important as the hardware. Staff brief each group, control spacing, monitor conduct, and keep rescue procedures ready for anyone unable to continue. The attraction sells freedom by stripping away visible barriers. That freedom lasts only while inspection, weather limits, train supervision, and continuous attachment never relax. A cliff that rejects a normal road carries 3 glass lifts straight up its face. They climb more than 300 meters from the valley to the Wulingyuan Plateau, partly inside the mountain and partly on exposed steel. That split route creates 2 different maintenance fronts. Inside, crews control moisture and drainage. Outside, they face wind, rain, runoff, and shifting temperatures. Yet the lifts must behave as one precise machine. Guide rails, doors, brakes, sensors, communications, and power must stay aligned across the full vertical run. Heavy visitor demand adds relentless operating cycles. Every opening door and repeated journey puts more wear into machinery that cannot be serviced from an ordinary street. The cliff itself also belongs to the job. Rock anchors and slope conditions tie elevator engineering to a sandstone face that weathers around the steel. A shutdown here is not a routine building problem. With no nearby stairwell, crews need access platforms, mountain routes, backup procedures, and reliable communications before work can even begin. The vertical route functions as a road only while it is inspected, drained, aligned, and repaired against the weathering cliff. On Mount Huashan, an entire mountain can depend on a single worn step. Granite summits rise more than 2,000 meters, while stairs, chains, ledges, platforms, and cable cars form the only linked access across terrain with almost no level ground. For centuries, these routes have carried pilgrims between Taoist temples and sacred peaks. Modern transport reaches parts of Huashan, but it does not erase the exposed connections between them. The famous plank walk is only one short, controlled section. Its lesson applies everywhere. When there is no usable ground beside a foothold, that small fixing carries the weight of the route. Rain turns polished stone slick. Moisture enters cracks. Winter ice strips away traction and can block the very paths repair crews need. Visitors add another force. Repeated footfall wears treads, while bottlenecks can force closures or controlled movement before a minor weakness becomes a mountain-wide access problem. Maintenance here cannot gather around one building. It stretches across a vertical network where tools, replacement fittings and workers must reach narrow sites before repairs can start. Huashan's critical structure is not one cable car or temple, but every stone tread and chain fixing that keeps the next peak reachable. Kalavantindurg's defining structure is not a fortress wall, but a staircase cut into the mountain itself. That route climbs a steep basalt pinnacle beside Prabalgad, rising from Thakurwadi through Prabalmachi before the exposed upper steps begin. The distinction matters. A prefabricated flight can be removed and replaced. These uneven treads are part of the rock, so erosion changes the route itself. During the monsoon, runoff follows grooves and footholds. It wets the basalt, loosens soil below, and folds the upper climb into rain and mist. The dry season changes the pressure, not the difficulty. Heat, limited shade, and water needs bear down on anyone carrying out inspection or access work. Near the top, there is little level space for barriers, rest points, or construction equipment. Opposing groups can meet on narrow sections and turn a small delay into a bottleneck. So upkeep starts with modest, relentless work. Clear drainage, mark the trail, inspect damaged footholds, maintain warning points, and close access when conditions deteriorate. Every worker, tool, and repair material must use the same constrained approach under maintenance. Remoteness makes even a small defect costly in effort. With few fortifications above, the carved route is the structure. Keeping those steps usable is what keeps the pinnacle connected. Here, upkeep is not preserving a spectacle. It is preventing isolation from returning. In 1977, villagers completed more than a kilometer of tunnel through the Tai Hang cliffs, using hand tools, drills, and controlled charges. Before that cut, Guoliang sat behind rock walls that turned ordinary travel into a serious daily obstacle. The tunnel was not a shortcut conceived for comfort. It was a working answer to isolation. Window-like openings solved two construction problems. They admitted light and ventilation, then gave broken rock an exit toward the gorge. Those same openings now admit wind-driven rain and fog. They also leave the roadway exposed to loose debris and the cliff edge. Inside, limited width, blind bends, and an uneven ceiling leave little room for vehicles to pass or crews to work. Every obstruction can interrupt residents, supplies, emergency access, and tourism at once. Drainage must remain clear. Rock must be inspected, unstable material removed, and traffic controlled while the only practical corridor keeps carrying daily life. The excavation ended in 1977. Exposure began the moment the road opened. If drainage fails or rock closes the lane, isolation returns, not as history, but as an immediate fact. At Maijishan, protecting a sculpture means holding an entire sandstone cliff together. Nearly 200 cave shrines and more than 7,000 Buddhist figures depend on exterior stairs and walkways fixed to soft rock. Work began around the late 4th century and continued under later dynasties. Clay, timber, stone, plaster, and paint were set inside vulnerable rock. Earthquakes have damaged caves and access structures. Rain can enter cracks, weaken sandstone, and shift humidity around surfaces too fragile for aggressive repair. Rockfall and biological growth add pressure. So does visitor movement, because every person reaches the shrines through structures attached to the same vulnerable face. Modern platforms solve access by creating another burden. Anchors, joints, barriers, and load paths must be checked where staging space is scarce. Crews monitor cracks, control drainage, stabilize weak areas, and restrict access when needed. A walkway repair cannot be allowed to harm the cave beside it. The art has no shelter separate from its geology. The same cliff holds both shrine and root. A failed drain can damage a sculpture. A failed walkway can remove the route to save it. Preservation begins with the cliff. Floodwater passes far below. The harder threat is any loss of fit where timber disappears into stone. At Jinlong Gorge near Datong, horizontal timber beams enter sockets cut into the cliff, carrying compact halls, stairs, and balconies across a narrow rock face. Some visible posts provide added support, but they do not carry the whole explanation. Much of the load travels through hidden timber and rock connections. The setting offers protection and pressure at once. The overhang blocks direct rain and intense sunlight, while elevation kept the buildings above gorge floods. But the cliff removes the room normally needed for repair. Timber, roof tiles, tools, and scaffolding must move along narrow galleries with almost nowhere to stage them. Crews watch weathered wood, shifting joints, water in rock sockets, visitor loads, and the cliff itself. A weakness in one material transfers pressure into the other. Access is also part of what must be preserved. Buddhist, Taoist, and Confucian shrines share one compact route, so a closed gallery can break the meaning of the whole arrangement. The dependence is exact. Stone must grip the beams, and timber must carry weight without losing its fit. No material can be conserved alone here. Survival is measured joint by joint. One small temple roof on a sliver of granite demands a maintenance effort far larger than its footprint. On Taiyun Mountain in Shanxi, halls, gates, and a summit shrine occupy a narrow ridge with almost no room for storage, scaffolding, or error. Everything needed to keep the complex working must climb mountain paths and stairs. Timber, tiles, tools, food, and water move in loads small enough for the confined route. That difficult access shapes every repair. Materials cannot be spread across a broad courtyard. Crews have few secure positions, and work must share the ridge with visitors. The weather reaches it from every side. Wind lifts at exposed roof edges, lightning threatens the highest structures, and winter freezing can open joints in stone and masonry. Water creates the quieter pressure. A blocked drain can drive rain beneath roof tiles or toward a stone base, turning one neglected channel into damage below. Modern walkways ease the approach, but they do not end the burden. Railings, anchors, metal fittings, and joints add another layer that crews must inspect and secure. Taiyun endures because small repairs never stop. On this granite ridge, keeping one modest temple roof in place requires a permanent commitment to reach it, inspect it, and repair it. A fortress commanded the plain, yet its hardest requirement was not stone. It was water. Sigiriya rises about 180 meters above central Sri Lanka, where a 5th century royal complex had to move people, materials, and supplies to the summit. Height delivered protection, but charged a daily price. Every stair, passage, and steep approach restricted the movement needed to occupy the rock. The lower gardens answered with hydraulic control. Channels and fountains used slope and pressure, while summit cisterns held water where no natural stream crossed the top. That engineering bargain still governs conservation. Tropical rain feeds plant growth and erosion, while uncontrolled runoff can reach vulnerable masonry and painted surfaces. Water must be held where useful and diverted where harmful. A neglected channel shifts pressure elsewhere across the vertical site. Movement creates a second strain. Thousands of footsteps wear stairs and narrow circulation points, yet those same routes must carry inspectors, tools, and repair materials. Preserving Sigiriya means more than stabilizing summit ruins. Crews must link rock faces, frescoes, vegetation, channels, paths, and structures from plain to crown. The summit cistern exposes the bargain. Power claimed the height, then had to keep it supplied. Command of the rock was purchased with permanent control of water and the road upward. 14 gates made one mountain road hard to penetrate and hard to maintain. Berg Hokosterwitz rises about 160 meters above the Corinthian plain, its steep ascent serving as supply line and defensive barrier. Each gate forced movement to slow, turn, and cross confined ground. That geometry strengthened the fortress, but controlled every ordinary load moving uphill. Food, water, timber, tiles, and tools followed the same climb. Repair crews still depend on that road before any work can begin above. Each gate adds more than stone. Timber, doors, hinges, roofs, and drains that weather can loosen or saturate. The road carries a wider burden. Runoff must leave the surface without cutting into the slope or weakening retaining walls beneath the route. Seasonal freezing opens small faults. Vegetation presses into joints, while repeated foot and vehicle traffic wears the very path needed to bring in the next repair. The key logistical fact is blunt. The fortress stays serviceable only while its obstacles remain passable. A damaged bend or blocked drain below can delay repairs far above. Hokosterwitz turned a limestone slope into defense, but it never abolished the climb. Its survival rests on keeping 14 gates and one steep road ready to carry every repair uphill. Isolation was Meteora's purpose. An uninterrupted supply line is now its condition of survival. Since the 14th century, its churches and cells have occupied sandstone summits cut off by steep rock faces. Every delivery once became a vertical lift. Food, timber, people, and roof tiles rose in rope nets, baskets, and hoists. Cable systems still serve points ordinary vehicles cannot reach. Modern stairs and bridges ease movement, but they do not create broad service roads. Crews still depend on narrow approaches, exposed terraces, rock anchors, and equipment carried across the height. Rain creates another burden. Water must leave roofs and terraces quickly without cutting deeper channels through the sandstone beneath them. Each material responds differently. Tiles shift, plaster traps moisture, painted interiors need stable conditions, and retaining walls carry weight on ground that weather keeps weakening. Visitor pressure adds wear inside compact rooms and stairways built for monastic life. Conservation therefore extends beyond the summit buildings to every route that supplies them. Centuries later, conservation still succeeds only when access, drainage, stonework, and skilled hands move together. Here, even a roof tile becomes freight across open height, and every intact room records a supply line that succeeded. The wet cliff above Sumela is not a backdrop, it is an active threat. Around 1,200 meters above the Altendaire Valley, rain, freezing, and unstable rock strain the buildings and their approach. The humid forests of the Pontic Mountains keep water moving through the site. Rain feeds vegetation, enters masonry and rock joints, then reaches vulnerable plaster. Winter ratchets the damage outward. Each freeze enlarges wet joints and leaves more room for the next storm. That pressure reaches the rock-cut church and its frescoes. Painted surfaces cannot remain stable if roofs, courtyards, channels, and the cliff keep sending moisture toward them. The aqueduct, cells, kitchens, and storerooms depend on the same discipline. Catch water, redirect it, inspect the joints, and return after the weather changes. Rockfall makes repair larger than the monastery. Crews must monitor the slope, secure unstable material, control vegetation, and restore access routes before work inside can continue. Modern visitors add wear in passages never designed for crowds. Here, art conservation and mountain repair are the same job. Wet forest, cliff, and masonry share only a few stable meters. Every storm tests how long those meters will hold. Sacred Isolation has a daily freight bill at Tiger's Nest. Above 3,000 meters, the cliffside monastery has no road and is reached only by a steep trail, descending stairs, and exposed approaches. The route carries two flows. Pilgrims approach an active place of worship, while workers bring food, fuel, tools, and repair materials over the same ground. Altitude slows every load and repair. Less material arrives at once, physical work takes longer, and a blocked trail can delay the whole site. Rain, mist, wind, and winter decide when that chain can move. Wet stone reduces footing, while exposed stairs leave little room for bulky cargo. Water creates work, even after a delivery arrives. Roof runoff and cliff drainage must be directed away from masonry and timber joints before moisture spreads into the buildings. The major fire in 1998 exposed another weakness and led to extensive reconstruction. Continued operation now depends on prevention, communication, inspection, and controlled movement through confined spaces. The decisive detail is ordinary cargo moving along a route that weather can close. The day's worship begins long before the doors open, with meals, tools, roof timber, and workers climbing the same exposed trail. A refuge built to protect climbers can be shut down by one ladder buried in ice. Cabane de Bertol stands at roughly 3,300 meters on a rock outcrop so narrow that the hut rises through 4 levels instead of spreading sideways. Above the Arola Valley, steep steel ladders fixed into the rock form the final access. Snow buildup, damaged rungs, or loose anchors can interrupt the route to the entire building. The hut supports climbers crossing glaciers and high passes, yet food, fuel, water system equipment, and replacement parts cannot arrive by road. Major loads need specialized mountain transport. Smaller jobs face the exposed approach. Inside, altitude enters every routine. Pipes can freeze, water is limited, wind-driven snow works into weak points, and moisture from occupants must escape without losing heat. Forecasts control deliveries and staffing. Short operating periods compress stocking, waste handling, inspections, and repairs into narrow windows, while storms can close those windows without negotiation. Very little separates refuge from closure. A blocked ladder, a failed pipe, a delayed load. At lower altitude, each is a routine service call. Here, each can stop the whole facility. At 3,300 meters, a sound rung or flowing pipe can decide whether the next climber finds refuge or a closed route. On Monte Cristallo, an entire shelter can depend on whether a single bolt still grips the cliff. Bivacco Buffa di Perero occupies a recess in a near-vertical wall at about 2,800 meters, with a ledge too narrow for ordinary scaffolding or a service platform. The shelter originated during the First World War as high mountain routes were established across the Dolomites. Its masonry, timber, sheet metal, and fastenings have faced high-altitude exposure ever since. Inspection begins before the door. Crews must reach the Ivano de Bona via ferrata with climbing equipment, then wait for weather steady enough to work on the wall. Freeze and thaw can widen cracks in the shelter and surrounding rock. Wind, snow, and water then weaken joints that are difficult to reach. Helicopters may carry major loads, but they cannot remove the cliff from the job. Visibility and low wind must align. Every load still has to meet a narrow ledge. As an old bivouac without normal staffing, The shelter cannot report weaknesses as they develop. Its condition must be checked, connection by connection, whenever access becomes possible. At Buffa di Pereiro, the walls matter, but access to each damaged bolt matters more. A mountain inn can serve a full dining room and still have no road to its door. Aesir occupies a narrow ledge beneath an overhanging wall in the Alpstein range. Access depends on the Ebenalp cable car, the wild Kirchley cave route, and a final mountain path. That route is also the inn's supply line. Food, cleaning materials, staff, repair parts, and outgoing waste must all fit the same access limits as the guests. The overhang blocks some rain, but does not solve the mountain. The facade takes valley weather. The rock behind leaves little room for drainage or service access. Poor weather can make narrow trails unsafe, just when the building needs attention. A blocked drain is no quick call-out. It becomes a transport problem. Seasonal opening is not merely a business choice. It compresses inspection, stocking, repair, and closure work into the periods when cable car schedules and mountain conditions permit movement. Hospitality runs on calculation. Guest numbers against food stocks, staffing against transport, water use against waste removal. If one link slips, service feels it immediately. There is no back door. Every full dining room has already required workers, supplies, and waste to pass the same mountain route. This bridge stays aloft by trusting supports that are alive, wet, and always changing. Seven suspension spans run about 350 meters through Kakum National Park, some 40 meters above the forest floor, on a deck barely 30 centimeters wide. Concrete piers would separate the crossing from the forest. Kakum does the opposite. Cables and anchor points share their load with tall rainforest trees. That choice creates the real engineering problem. Trees grow, flex in wind, hold moisture, and weaken under insects, fungi, or biological stress. The walkway cannot be inspected as steel and timber alone. Crews must also judge the condition of the living trunks carrying it and whether the anchor points remain sound. Heavy rain works into planks, ropes, netting, cables, and connections. Wet footing and daily visitor loads keep adding pressure, week after week and season after season. Repair is constrained from both sides. Materials must reach a narrow route high in the canopy, yet replacement work cannot scar roots, cut trunks, or clear unnecessary access through protected forest. Kakum sets a stricter test than durability alone. Keep the bridge usable without replacing the living forest with concrete. A navigation light built for the hardest point to reach is useless the moment maintenance cannot reach it. The present lighthouse was rebuilt on that isolated Aegean rock in 1994, after the 19th century original was lost during the Second World War. There is no road, harbor, or broad platform where crews can stage tools. Every inspection begins with a boat and a narrow window of manageable sea. People and equipment must transfer beside exposed rock, then finish the job before rising wind or waves close the return route. Salt spray does not need a major storm to cause trouble. It reaches metal fittings, doors, railings, electrical enclosures, and the equipment that keeps the light working. Repeated wetting and drying also strain masonry and joints. Automation removes the need for permanent occupation, but not for cleaning, power checks, inspection, or corrosion control. That is the central contradiction. The lighthouse marks a difficult coastal position precisely because ships need a fixed warning there, while the same exposure makes each repair visit uncertain. The compact tower is only the visible part of the service. Every reliable flash records a crew crossing the sea that makes the light necessary. Pisa can only be preserved by correcting its defect without correcting it completely. The nearly 57-meter bell tower began tilting during construction, as its shallow foundation settled unevenly into soft clay, sand, and silt. Its masonry kept loading ground too weak to respond evenly. Building pauses allowed consolidation, but later work continued around a tilt already fixed in the tower's form. By the late 20th century, movement and instability forced the tower to close to visitors. Its famous deviation had become an operating limit. Engineers used temporary restraints and counterweights before removing small amounts of soil beneath the higher side of the foundation. No part of that operation could be rushed. Controlled extraction allowed the tower to rotate back slightly. The goal was not to make it straight, but to reduce the lean without erasing its identity. Every step required continuous measurement across masonry, foundation, and ground. Removing too much soil or moving too quickly could shift the load and create fresh instability. Monitoring continues because the soft layers below remain part of the tower's behavior. Pisa proves that the right repair can mean preserving a deviation, then controlling it without pause. I began with the assumption that scale was the main measure of engineering power. It is not. The harder test begins after opening day, when water finds joints, salt reaches cables, foundations move, and mountain weather cuts supply routes. In remote terrain, maintenance is not support work. It is the structure's second foundation. That changes how these places should be judged. A dam, bridge, monastery, shelter, or tower remains possible only while people can inspect it, carry material to it, and act before a small defect spreads. The warning is concrete. Building farther into resistant terrain creates obligations that may last for generations. The power of this construction age will not be measured only by what it builds, but by what it can still reach, repair, and keep useful under pressure. Follow this documentary series as I examine the hidden labor that keeps remote engineering operational and the limits exposed when access, weather, and terrain begin to outrun repair.